Now let's start to go into a more practical sense of the things that you are likely more interested in. As I mentioned during the presentation and as just showed you, there are small variations. We know that the OTE has been very stable in the past few months since April, but eventually sometimes we have abrupt changes where some segments may move because of thermal instabilities. Say very small changes. So let's say the first thing you want to do, you just got your set of observations and you want to see how was the telescope performance during a particular time, during the particular time of your observation. So in this example, for instance, I can use this function, the trending delta wavefront error around time, and I can set up a time where my observation was collected. I can see that from this, basically it takes the difference of these two OPDs that you see on the bottom with this image. And from this, it gives you the first idea on how stable the OTE was. And you say, well, why do I care about this? Well, this is the first set of you to say, do I need to, let's say that you see something that doesn't look quite right on your images, that your PSF looks a little bit different than you would expect, then the first thing you want to check is to make sure that during your observation that there were not any of these thermal instabilities that could have moved or compromise a little bit the OT quality of your observation. So this is the first step, right? You just want to see how was the OT during your observation. In this case, the OT was very stable. There are not large variations. The ones that, for instance, I showed you in the presentation, when you have some of these phase maps and some of these segments looks more red or more blue, right? Which is the scale of it, will have a higher wavefront error. That means that's likely something happened on those observations, which is not intrinsically a problem because we do have the OPDs for those times. So even if you have, let's say, an ugly PSF in quote, you always have a way to model your ugly PSF. So if you're going to subtract a PSF, you'll subtract just an ugly PSF, if that's the case, right? However, we do have, I just show you how to set up a simulation completely, but there is now a very convenient function that allows you to set up everything that I just did manually. You can do that automatically by running a particular function in WebbPSF that is going to grab your observation, either your cal fit, your level 2B products, or your I2Ds, your level 3D product, level 3 products of the pipeline, and use the information that is in the header and use that to set up your observation directly. So for that, and this is something that you may want to keep as well, I think this is a good sort of like Easter egg on this notebook. I have this function that I just call mass retrieve file. And this function allows you to download any file from the mass portal directly. As long as you have the correct name of the file, you can always use this function. So if you know the name of the file, and you can get the name of the file from the mass query, or if you know how these files are being named, so you can guess the naming file, the name of the file. You can always use this function. So this is a useful function to have. It allows you to input a token, especially if your observations are restricted. So if you are the PI, if you create your own token, you should be able to download your own observations. So in this case, let's run this cell to define this mass retrieve, and then just retrieve one of the files that we get when we do our maintenance sensing program. And this is this particular file. In this case, I already have downloaded the file. So if you haven't downloaded the file, it's going to show you downloading the file, and you should have that file now on your local folder. So now with this file, remember that I have the file, and basically with this file, I'm going to use this function that is called setupSym to match file. It's one of the new functions in WebbPSF, and everything that I did before, where I set up the instrument, where I loaded the OPD for a date, all that is going to happen automatically by filling all those parameters from reading that file. So in this case, we just set up, we use the setup sim to match file. It's going to set up my instrument class, and it's going to do exactly as we did before with a single function. As you can see, is setting up for NIRCam at 2 microns A3. I mentioned that A3 is where what we use to do the calibration of the telescope. And in this case, we're using a weak lens image. This is the images that we use to do phase retrieval or focus diversity phase retrieval. And we get our simulation. We get our PSF. This is our simulated PSF for the weak lens image looks from this. So basically what is going to happen, look here that when I did the setup seems to match, I can also pass my detector position, right? So the first thing I do is I basically just initialize my instrument class with all the information that is inside the feed file header. But outside that, once I do that setup, I can have the position that I want for the PSF that I want. I can either include or change my detector effects, and then I can just run my PSF simulation. So I can see that, for instance, you have your own file and you can test this locally in your computer. You have your own file. Just do this to set up your simulations and you'll have already your simulated PSF. So I just want to get that out of the way early because this will be the most convenient way for you to set up your simulation. Now, there are a lot of things that goes into that function. So if you have a very particular observation that you find that using this function doesn't give you the correct setup, then please open a GitHub issue and let us know so we can add more rationale into this function so we can capture all the different combinations that may exist for us to set up to have the right configurations. Um, and in any case, moving forward, so that's how you set up your observations using the OPDs. And I wanted to show you just quickly because then we can jump to other parts of the notebook. How do you train the optical performance of the telescope? I mentioned that this is important because let's say that you are combining in your work, you have observations, you have a large program that have observed the sky at different times, right? And then you want to see how different were the PSF across that time. You want to see if there was a large event that affect a set of observations and not the other one, etc. Because that's information that is going to help you set up your simulations eventually. We have a convenient function if you want to see, for instance, how the telescope was trending over a particular month. For convenience and to sort of like not brag because I'm not the telescope itself, but to brag about how good the telescope has been behaving, I just choose June. So last month was a very stable month. So I'm going to run this cell and be careful because you'll see later on the notebook that don't try to run all the cells that I have following this one because some of these cells will try to run for the entire OPDs that we have for the sensing program. So that can take a long time. Those are intended if you're really curious about the long-term performance of the telescope itself. So don't try to run all those cells right now because it's going to take you some time. If you run it, nothing happened, just stop the code because it can take longer than a few minutes. Stop and rerun, restart your kernel and rerun everything again. And we'll see that in a second. But in any case, this is the sort of things that you can trend on WebbPSF now. We have improved a lot of the trending functions that we have. So you can take a look at the optical performance of the telescope. In this case, we have the measure wavefront maps or the phase maps that you have, and the drift, basically how much they change between one measurement and another one. In other words, how much the optical performance of the telescope change in a period of about 2 days or so. And you see so basically it's a difference between the phase maps. And you see that on the second row that we are almost flat all the time. In this particular month, we were very stable. You can see the change on the circle energy. We were the circle energy almost didn't change during the month of June. And that has been the case since April, right? So you're lucky if your program got observed during these extremely stable periods of time. But in any case, this gives you an idea on how was the telescope behaving during that time. Note that these metrics, like in circle energy fractions, are measured on these simulated PSF based on the phase maps. That doesn't mean that if you measure your encircle energy on your actual observation, you'll get exactly this value. And in this case, this is simulated for the based on our sensing observation. So at 2 microns, I can do the same plot with different instruments if you're trying to see the trending different instrument. What I say is like this encircle energy applies to this simulated PSF. Likely things like signal to noise on your simulation, contamination from neighboring stars, all those things will factor in when you do your encircle energy. So don't try to match this one-to-one to what you observe, but this gives you a good idea of the performance of the telescope, right? So this is not intended for you to match exactly what you should be observing because ultimately these are simulations. Now, when I do this create a table. And on that table, you can see the time, the date on when those observations or where that phase map was created. So the time of that optical performance of the telescope at the time, the type of observation, these are sensing. We have sensing and control. Control is when we move the mirrors to maintain the alignment of the telescope if needed. We don't apply those that often. Just depending on the optical performance. And we have basically all the information that was used to populate these figures are on this table, right? So you have access to these if you want to keep that to yourself. Now, there are other things that we can do, and this is the part where I would not run all these cells. You can run this first one because this is going to give you a table of every single phase map that is available on the mass portal. And note that every single OPD that you'll find in the mass portal is, we make an effort that every OPD that make it to the mass portal is the correct OPD for that time. So everything that is there, it should be a final, curated, well-kept list of OPDs. Right? And you see here that you create this very large table. In this case, it have more than 500 OPDs, starting early in commissioning. This is when we did our first phase of the telescope, when we were starting to do the phasing of the telescope, of the mirrors. And you have different informations about, for instance, the OPD file. Remember before you could have load these OPD files manually. So this is where you can get some of that information. And it gives you information about the type of measurement that we were doing and if this is before or after we apply a correction. So you have a lot of information here, and this is a complete list of OPDs. Now, there is a convenient function. This is the one where you don't want to run here on this notebook that allows you to download pretty much every single OPD. These have a couple of relevant cases. Let's say that you want to see the long-term performance of the telescope because you have different programs that you are looking at and you really want to see how the telescope has been behaving since early in commissioning. You can download these. Once you download these files are saved inside that WebbPSF data folder. Once you download this file, then you don't have to download those again. So you can always play with these OPDs. We're going to see later that maybe you have an observation from your program and you want to compare that with another program just to see if the PSF change or anything. You have access to all those OPDs if you decide to download everything. So don't run this right now because it's going to take some time to download all the 500 files. But really, once you have those, then you should be good to go for any simulation that you want to test. I did run this so I can show you the long-term variability of the OT, but you don't have to do this. But let's say that once you have that, then you can create figures like this. This is all the wavefront errors for the entire since commissioning to basically to this past weekend or last week when I ran this notebook. And you see that despite a few very particular cases that we were able to correct quickly, there is very small variations in the wavefront error. Now remember, this is the global wavefront error of the telescope. This doesn't translate necessarily to big changes on the properties on the PSF that you're going to be interested on, either the circle energies, thread ratios, or full width. This doesn't correspond to this degree of changes, right? We know that this global wavefront error is related to the PSF properties, to the properties of the PSF. But don't be scared, like even if you see big changes like this, that doesn't mean that your PSF was completely destroyed. It just means that it just changed a little bit, but you do have access to those OPDs. There were cases where the PSF truly got destroyed. And we have some of these very large cases here. One of those, I show you the link on the presentation about this memo for this large event that happened early this year, where we have one of the segments had a phase wrap and there was needed to have a large correction. Now, the good thing about these events is that, yes, they can change the PSF a lot on a very particular time period. In this case was like a day or so, but there are a couple of positive things about this. If sort of this is the silver lining of this. One of the positive things is that all these events that are related to thermal variations can be corrected almost 100%. So basically, after correction, we go back to the optimal performance of the telescope. So there is not a problem there. And the other thing is that if indeed your science case was affected by these very specific events that you see, these are not that many, there are only a couple that truly change the PSF, you can always reach out to the Institute and request a redo of your observations because the quality of the telescope was not optimal. These have happened only a couple of times for very particular events. So you can always reach out, for instance, to the WebbPSF help desk. And then if you are in doubt, just say, listen, these are my observations. I look at the performance of the telescope. Apparently there was a big event that happened during that time. And then we can advise, we can suggest many things and work on your data. And eventually, if needed, you can always request to do a redo of the observation. So these are the options that you have, and this is very particular to not necessarily WebbPSF, but to your program in general. But WebbPSF will help you assess the situation, right, that you are on it.